Hey, so now that we've gotten kind of comfortable with the idea of experimental and theoretical probability and how to kind of compare the results of an experiment to maybe what we would have predicted would have happened to begin with, we're actually going to look now at something called compound events. Earlier in the unit, we only were looking at the probability of one thing happening at a time, but now we're looking at the probability of two or more separate events. That's what we mean by compound. Same thing like in a compound sentence in English class is it's a sentence that's joined by the word and. So here with compound in math, we're saying that it's the probability of this event and something else occurring. Now we're going to define the two types of compound events as either independent or dependent, and that's what the title of today's notes are. I can determine the probabilities for both independent and dependent events, all right? Now, if the outcome of the first event will impact the outcome of the second, that's dependent because what happened the first time is going to impact what happens the second time. Now, if the outcome of the first event does not impact the second event, then that's going to be considered independent events, okay? Now we're going to explore kind of here the difference between independent scenarios and dependent scenarios. Again, independent, what happens in one should not affect the other. Dependent, what happens in one will affect the other, okay? So the first independent scenario that I have here is that if we flip a coin and spin a spinner, these are the two events. One event, we're going to be flipping a coin. The other event, we're spinning a spinner. Now I have here, this is me flipping the coin. When I flip the coin, it doesn't matter if I get heads or tails. That will not impact whatever happens down here when I spin the spinner. So because the result of this first event has absolutely no impact on what's going to happen here, these are separate independent events. Okay, so that's why that's listed here under independent. Now to calculate the probability of flipping a coin and spinning a spinner and seeing what happens here, like the probability that I land on tails and get an even number. Now the probability that I land on tails, I'm going to put the probability in this first blank. The probability that I get an even number when I spin the spinner is going to go in the second blank. So the probability that when I flip the coin, it lands on tails is a 1/2. And if there's a spinner numbered 1 through 4, let me pull my spinner back up here. And it's like a 1, a 2, a 3, and a 4 here. And I want to know the chances that I land on an even number. Well, that's going to be 1/2. So that's a 1/2 as well. So to find the probability that I'm going to get tails and an even number, I'm actually just going to multiply right here, and that's going to be a 1/4. Now I'm going to use this example real quick to just kind of show all the possibilities and how the probability that I get tails with an even number is 1/4 of the time. So coming back to this, I know I could land on heads and then get a 1 on the spinner. I could land on heads when I flip the coin and then get a 2 on the spinner. I could have heads when I flip the coin and land on a 3 on the spinner, or I could have landed on heads here and then a 4 on my spinner. Or basically, it could have been the same thing just if I had landed on tails first. I could have gotten tails, then a 1. I could have landed on tails, then gotten a 2 on the spinner. I could have landed on tails, then gotten a 3, and then landed on tails and gotten a 4. So these are all of my possible outcomes. There's 8 possible things that can happen here. Now that being said, I wanted to check for the probability here that I'd land on tails and then followed by an even number on the spinner. So the chances of me landing on tails followed by an even number are right here and here. These are the 2 possible outcomes out of the total 8 ones. So that right there reduces to 1/4, and that's the answer we got on our notes. So to get this answer very efficiently without having to list everything out, you can just take the probability of the first event and multiply it by the probability of the second event, and you will then have the probability of the compound event. Now, another really popular example of an independent scenario is if you're going to pick a card from a deck of cards and then replace it. So for example, if there's 52 cards in a deck and we want to know the probability of selecting a red card. Well, the diamonds and the, diamonds and hearts, that's half the deck is red. So for this one, we're also going to have another 1/2. And if I put the card back in, then half the deck is still red for the second draw. So there is a 25% chance that I'm going to select 2 back-to-back red cards if I replace the first card. Now you can see the next example that I have right here for dependent is, let's say when you select that first card, if it's red, let's talk about how it changes if we don't put that card back in. Now we know again, half the deck was red. I'm just going to put half, so 26 out of the 52. So half the deck. And I guess it makes sense just because we're talking about the color red for the problem. So let me just make that red. Why not? So half the deck is red. And then again, for the second draw, we said that there's still half the deck is still red. And I could just reduce here the 26 out of the 52. I just reduced it so that my answer would already come out reduced. Okay. Now over here, the first probability is still that half the deck is red. 26 out of the 52 cards is red. And for the second one, if you don't replace it, think about it. One of the red cards is already out of the deck. You already drew one out of the deck. So there's only 25 red cards left in the deck. And there's also one less card total right here. So that's how these things change. Notice that for independent scenarios, the denominator over here is still the same because I'm not going to keep the card. I replace it, so it's still in there. But if I keep the card, then there's one less right over here. So when we do the probability of this, we can multiply across like we could have here and have a very large answer to reduce. So for example, 26 times 26, that would have been the numerator over here, and then the denominator. Whoops. So 676, oh my gosh, sorry y'all. 676 over 2704. Nobody wants to have to reduce that. I can divide it to prove to you guys right now that it is 25%, but none of us feel like having to reduce this. See, it is the 25%, so I know it's a 1/4. None of us want to reduce this crap. So the reason I'm pointing that out is because over here, instead of setting yourself up to have to reduce a massive answer in the end, all I'm going to do now is simply swap out that I know 26 out of 52 is a half. That is a 1/2. So now when I multiply across, I've got 1 times 25 and 2 times 51. And this answer is already reduced. I don't have to reduce anything. And I can just put it in a calculator to kind of compare real quick that if we don't replace, it doesn't jump by much, but it drops down to a 24.5%. It drops down a little bit only because there's one less red card. So that makes sense. There's one less red card, so our chances aren't as good as if we had kept that card in there. And again, you could see 24.5%. It's basically 25%, so the math here, it's very similar. But yeah, it's slightly less here than it would have been. Now, another dependent scenario is actually locker combinations. And the reason the locker combinations are dependent is because, and that's what I have this picture over here for, this is dependent because locker combinations are comprised of 3 numbers. And whatever number you get for this first spot, like whatever number is here, locker combinations never have the same number repeating back to back. So like if this number in your locker combination was a 22, this number will not be a 22. Okay. So there's 50 possible things on the locker combination. It's numbers 1 through 50 or 0. Actually, it's 0 through 50, I think. So if it's 0 through 50, there's actually, it could also be 0. So there's 51 things that it could be in this first spot. But then there's actually only 50 possible numbers for the next spot because remember, one of them already got used. So this is going to be any number that's not a 22. But then this goes back here. This could be this number again, but it would not be this number again. So it could be, for example, you could have a 22, 4, 22. That is a locker combination that is possible in the school. But my point is that whatever number gets used here first, it's not an option for this second number. So there's only 50 possible numbers that could go here. And then because these don't repeat back to back, there's 50 numbers that this could be as well. So this is a dependent scenario here. This is definitely a dependent scenario. And even though in the notes right here I say what's the probability that your locker combination is going to be multiples of 5, what I mean is I don't want to overcomplicate this. This is a really tough example, but out of all the locker combinations in the world, multiples of 5 would be things like if you had a 5 in the first number here, you could have a 10, you could have a 15, you could have a 20, you could have a 25 for the first number in your locker combination, a 30, all the way up to 50 basically. So 35, we're almost done, 40, 45, and then 50. So these are all the possible numbers that are multiples of 5. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them out of 51 possible numbers that we said are on the locker. Now, for the next number to be a multiple 5, remember, one of these is already going to be used. So let's pretend the 40 already got used. Now there's only 9 of them that are left, and there's only 50 potential numbers because this is no longer a potential number for the second thing in the locker combination. Now, for the third thing in the locker combination, it's not going to be whatever the second number is. So like, let's pretend the second number here ends up being a 25. It can't be that number, but it could be the 40 again. So there's still 50 things here. Both of them aren't knocked out. There's still 50. And it could be this number that repeats. It just wouldn't be able to be the 25. So this is how the math would shake out to see how many realistic possible locker combinations there are if you were only trying to select for multiples of 5. Now, I wanted to show you this example because I wanted to mention that cross-reducing is a thing. Instead of multiplying 10 times 9 times 9 and getting 810 up here, and then having all these numbers to multiply and having to reduce, there's this thing out there called cross-reducing that says if you spot that this 10 can go into this 50, 10 goes into itself once, and 10 goes into this 55 times. That's going to help us reduce our answer because now in the numerator we just have 1 times 9 times 9. So basically we're already reducing if you want to think of it that way. But now we're going to have an 81 here, and then whatever 51 times 5 times 50 is. So 51 times 5 times 50. So 81 over 12,750. As you can see, the likelihood of that happening, of you getting 3 back-to-back-to-back multiples of 5, is very low for a locker combination. It's very rare that we're going to hear somebody say that their locker combination is 15, 30, 45. Very rarely is that the case, and you can see right here that the chances would not be very good. So I just kind of walked you through some examples, and I know that the math, we're going to focus on the math throughout the remainder of the video, but to just kind of reset on the fundamental part of like independent versus dependent, here we go. Dependent events are when the outcome of that second event is impacted by the outcome of the first event. Over here, that second event was impacted by this very first event. But for independent, the outcome of the second event is not impacted by the outcome of the first event. Again, remember what happens when I flip a coin has no impact on what I'm going to land on when I'm spinning a spinner. Same thing with a replacement. If I have a deck of cards, if I put the card back in, then whatever happened the first time around should not have any impact on that second draw. All right, so we're not going to worry about any math for this next part of the video. No math. We're just going to try to decide, would the event be independent or dependent, okay? Are the two events independent or dependent? So let's say you're going to roll a dice and you're going to toss a coin, all right? Most of these things, remember, with the number cube, that's just 1 through 6. So you're either going to land on a 1, 2, 3, 4, 5, or 6. And then over here, you're either going to get heads or tails. These are going to be independent events because what happens when you roll the dice should have absolutely no impact on what you get when you flip the coin. So for this one, I'm going to put a capital I for independent. These are independent events. Now for B, it says to take a marble out of the bag, and then it says to take a second marble out of the bag. Now the question we have is, did we put it back in or not? And it doesn't say. Now in this situation, what I want you guys to look at is right below it. Take a look at D, just this setup over here for D. Notice that in this one it says we're going to draw a card from the deck and put it back. Then we're going to draw from the same deck again. So it's going to tell you if you're putting it back. And if you put it back, this is independent because you have not changed the deck of cards for that second draw. So back up here for B, since it doesn't say we're going to put it back, we can assume we do not put it back. Therefore, there's one less marble in the bag. So you have now changed the number of outcomes for that second draw when you're drawing the marble out of the bag the second time. So therefore, our denominator would change, and this is dependent. All right, now if we're going to choose a person from a group of 50, that means that that person has a 1 out of 50 of being selected, okay? Now I'm going to choose another person from that same group. Now if I'm choosing from the same group, one person's already gone, so there's only 49 people left. And then again, anybody would have a 1 out of 49 chance of being selected second. So again, because here the denominator changes and it's the same group, and again, you can kind of think we're not replacing that person. This is another example of dependent. When your second denominator changes, you're automatically looking at a dependent scenario, okay? All right, cool. So now let's just kind of get comfortable deciding independent versus dependent. And then we're also just going to calculate. We're going to go back and practice the math for calculating on this page here as well. Okay. So for this first one, 2 seniors are one from each government class are randomly selected to travel to Washington, D.C. So it looks like there's 2 different government classes. Wes is in a class of 18, while Maureen is in a class of 20. So we want to know the probability that Wes is going to get selected from his class and that Maureen is going to get selected from her class. Now, since these are 2 separate classes, these are actually going to be independent events, because what happens over here in Wes's class, he has a 1 out of 18 chance of getting selected. Him getting selected or not getting selected out of his class has no impact on whether or not Maureen would get selected as the 1 out of her 20 in her classroom. So these are independent events, and this is the math for how we calculate them. So I'm just going to kind of move that over here. So if we're trying to calculate the probability that Wes and Maureen are the 2 students that get selected, it's going to be a 1 out of 360 chance. Okay. Now in the next class, or the next problem, I put this one back to back so that you could kind of see the difference. This time there's only 1 government class, and Wes and Maureen are in that same class. And in this setup, if they're in the same class that only has 38 students, again, if we're trying to find the probability that these are the 2 that get selected for the field trip, now this is dependent, okay? This is dependent. And the reason this is dependent is because Wes has a 1 out of 38 chance of being selected. And once one student's already selected, now Maureen, there's only a 1 in 37 chance for her. She's not fighting against the same 38. There's only 37 kids now in the class for her. So this is why this is now dependent, because the denominator changed. And when I multiply 38 times 37, it's 1406. So we get a 1 out of 1406 chance. Now I want to compare the percentages real quick. If I do 1 divided by 1406, oh wow, that's really small. Let's try that again. 1 divided by 1406. Let's see if I was right. Yeah. Okay, so this is a 0.00007. That's what that times 10 to the negative 4 meant. So this is the chances that Wes and Maureen are going to be the 2 that get picked, versus if they were in separate classes and we wanted that to be the pair that got picked. 1 divided by 360 here is 0.002. So there's a 0.2% chance that Wes and Maureen are the 2 that get selected. Like, let's just pretend that Wes and Maureen are dating. Let's just pretend. And they're like, oh man, what are the chances we're going to be the 2 that get picked to go on this field trip? So if they're in separate classes, there's a 0.2% chance that they're going to be selected. But if they're in the same class, It's actually even less. It's a 0.07% chance. So it's in their best interest that they're in separate classes to try to both get picked, because the chances that they both get picked from the same group, we could see right here, it's even less. All right. Okay, now we're going to take a look here and we're going to find the probability of these two events. First, we're going to actually be rolling a number cube and then another number cube. So basically, we've got these two die that we're going to roll at the same time, and we're checking to see like what's the probability that I get a 3 on one of the die and then a 4 on the other one. So the probability of us landing on a 3, we know that there's a 1 out of 6 chance of that. And then the probability that the other one would be a 4, there is a 1 in 6 chance of that. So you're going to have some luck here if you set things up by just drawing kind of two blanks for yourself and saying, okay, what's the probability of my first event? I'm going to put that here. And then what's the probability of my second event? I'm going to put that here. And then to find the answer, we just need to multiply. So 1 times 1 is 1. And then 6 times 6 is 36. So there is a 1 out of 36 chance that you're going to get a 3 followed by a 4. Okay? Now I can actually show that result real quick. I have all the possibilities listed out right here. You could get a 1 and a 1, a 1 and a 2, a 1 and a 3, and so on. So out of these 36 possible things, the chances of us getting a 3 and then a 4 are right there. And that's the 1 out of all of the 36 options. Okay? All right, now the probability that we get a multiple of 3 and then a prime number. So I'm going to draw my two blanks for my two events. And multiples of 3. So the multiples of 3 here are just 3 and 6. So we have a 2 out of 6 chance of that happening. There's two options there. Now the prime numbers, now remember 1 is neither prime nor composite. 2 is a prime number because the only factors are 1 times 2. 3 is a prime number because 1 times 3. 4 is not prime, but 5 is. So this time there's actually half of them are prime. Now I want to review again my shortcut here for the reducing first, because as of right now, if you multiply across, you're going to have a 6 and then a 36, and you have to reduce this answer. Versus if you had already reduced this one, which is a 1/3, and then you reduce this, which is a 1/2. Here we can see 1/3 times 1/2 gives us the reduced answer of 1/6. So you can reduce whenever you want, really. And those are both times that you could possibly reduce, either at the end or right here you can reduce first and then multiply, and you're right at the answer. And for this one right here, I want to know the probability that we get an even number followed by a 3 or a 5. So here's the blank for the probability of an even number, and then for the event that it's a 3 or a 5. Now we know half of these are even for the first one, so the chances that I roll an even on the first one, that's half. Now a 3 or a 5, that's 2 out of my 6. So again, we can multiply first and get 2 out of 12 and then reduce. Or we can reduce here and say this is a 1/3. So if I do 1/2 times a third, that gets me straight to my reduced answer of 1/6. Or you can reduce here and still get a 1/6. Okay? All right. And now here we've just got a couple more problems. So for number 4, if you're going to draw 2 red cards from a standard deck and it's got without replacement listed right here, meaning you're not going to put the first card back in, would that be considered an independent or would it be dependent events? Well, if we don't put the card back in, that means there's only 51 cards for that second draw. So we are impacting the event, the second event. So this is going to be dependent. I'm just going to circle it, but you can put that word right here. You can list the word dependent right there. So these are dependent. And again, the reason it's dependent is because there's originally 26 red cards out of the entire deck. But then if you take one red card out, there's only 25 red ones left. And then there's also one less card in the entire deck. So in this case, both the numerator and the denominator changed. Both of them were decreased by 1. Okay. Now again, I don't know about y'all, but I'm not trying to multiply these things across. So I'm just going to reduce this first and say that this is a half. Half the deck is red. So the first number is a half. And then times the 25 over 51. 1 times 25 is 25. And 2 times 51 is 102. So that right there I think we actually calculated that earlier in the video. 25 divided by 102, it was slightly less than 25%. I think it was 24.5% of the time. All right, and now for this last setup, okay? So Brian has some cards that are the same shape, but they're all just different colors. And he's going to draw twice, okay? Now the probability of him selecting a yellow card is 40%. The probability of selecting a red card is 10%. So right now, we don't know how many cards there are total, but I know that 40%, I'm just going to put 4 out of 10, are yellow. And we've got that 10%, so 1 out of my 10 would be red. Now, for the sake of simplicity, I could say, all right, well, if I've got 4 out of 10, I know are yellow. 1 out of 10, I know are red. That's 5 cards so far, and that's 50%. So I can use that. This should be enough. I don't even know how many cards there are. We don't even know if there's 10 cards. We just know that 40% are red, or sorry, yellow, and 10% are red. So if I want to know the probability that we're going to select 2 yellow cards, that would look like this without all the words. It'd be like the probability of yellow, comma yellow. So go ahead and jot that down. And even though we don't know how many cards there are, we know that there's a 10% chance that he's going to pick yellow. And here, it doesn't say it, but in my video, I'm saying it now. We are going to put the card back in. So we're going to put the card back in and multiply again now by the 10% to see here what the chances are that it's going to be 2 back-to-back yellow cards. Again, we don't have any fractions. We don't even really need to see the fractions. We don't even need to know how many cards there are total. We can just say the probability of yellow is 10% times the probability of yellow again, which is 10%. And in a calculator, if we just do 0.1 times 0.1, that's 0.01. So there's actually only a 1% chance that that's going to happen. If only 10% of the cards are yellow, there's only a 1% chance that we're going to get back-to-back yellow cards. Okay. Now for the next question, what's the probability that Brian's going to select a card that's not yellow, replace it, and then select a card that's red? So we're going for something here that is not yellow, so not yellow, and then something that is definitely red. Now for it to not be yellow, I don't care what color it is, I just don't want it to be yellow. If yellow makes up 40%, I know that 60% is not yellow. Again, it doesn't matter how many there are, it doesn't matter what the other colors are, it's just 60% must not be yellow if 40% is yellow. All right, now if I want to know the probability of a red card, that is 10%. So earlier in the video, I've shown you that you're multiplying the fraction. It is also the same as multiplying the 2% or decimals here. So we're just going to do now the 0.6, the 60% that are not yellow, times the 10% that were red, and that's a 0.06. So there's a 6% chance that this would happen, a 6% chance that this would happen. So the idea here, what we're trying to get comfortable with is you're basically going to be multiplying 2 probabilities together. You just got to decide, is that second impacted by the first? In some cases it is, like here, this is a dependent situation where the second fraction looks a little bit different because it was impacted. Here, since these are independent events, we can just straight up use the probabilities and say, okay, probability of yellow times probability of yellow, and then here probability of not yellow times the probability of red. You can be multiplying decimals here, you might have to multiply fractions. It's kind of up to you, it kind of depends on the problem. What you guys are going to do now is you're going to turn over and you're going to look at the problems on the next 2 pages. And you're going to attempt these 7 problems, and then there's a few more over here. So it looks like you have 12 problems that you're going to try now, and then the answers go into a Google form. That concludes this video. Thank you for watching.